Okay. Thank you, Francois, for inviting me to do the opening talk. I'm going to combine two views in here, one from the view from the scientist's view, the other from the question, the perspective of what a policymaker needs to make decisions about sea level rise.
Can you hear him?
Yeah. Okay. Yeah. And don't hesitate to tell me you can't hear me. And try to give you a picture of some emerging research, which I'm conducting in conjunction with some colleagues. And this is, I haven't given this talk before, so I apologize in advance if it's rambling and coherent. It's probably a little long, but you can leave whenever you need to leave, and I'm just talking. So the critical thing for those of you who are not, oh, by the way, this, the material here, particularly at the end of the talk, was developed in conjunction with Chris Little, who got his PhD from the Geosciences department here a few years ago, then went on to be a PhD, a postdoc with me, and was also had the PEI STEP Fellowship, which is an interesting program that any of you graduate students should look into. It helps merge science and policy. And Roger Cook at Resources of the Future, with previous contribution from another postdoc of mine, Nathan Urban, who's now at Los Alamos. The fundamental issue is that IPCC, which is supposed to be presenting information, assessments to policymakers in a form which is useful to them, generally frames the question of uncertainty, or sort of the range of outcomes that we expect, in terms of the model-based range, which is the colored bar, the colored region around each of these projections. This is a projection of global temperature over the century. This is a projection of sea level rise. They generally present these ranges in terms of the central 66% probability. And that's something that you would think a policymaker might have interest in using. What outcomes are basically within 1 sigma, have a reasonable probability of occurring. However, when you talk to policymakers, you get different views. Some policymakers are interested in what's the worst case, what's the worst thing that can happen, what's really in the tails of the distribution of probability of occurrence. I was at a dinner last night with a bunch of people from the financial community, including 2 former Treasury secretaries, and they had completely disparate views about what information was useful to them in judging risk, not just climate risk, but financial risk. Some wanted to know about the black swans, you know, the really bad stuff that you really can't put a number on in terms of the likelihood of it happening. Others want to know what's sort of in the middle, like this, and forget about the tails, because I don't know what to do about the tails anyway. I don't know what public policy to make to address the tails. So for instance, I'm on a committee that Mayor Bloomberg, former Mayor Bloomberg, put together to analyze the risk of climate change to New York City. It was particularly interesting in the wake of Hurricane Sandy, and we presented projections of sea level rise to the city. And we wanted to give them, you know, a whole 5 to 95%, you know, what's the central 90% of outcomes. They said, forget about it, just give us 25 to 75, because something that's at the 5% level will be so expensive to adapt to that we don't have that kind of money. We're just going to guess that we're not going to have to deal with it. Not necessarily a very smart view, but that's the way the public policy works. Anyway, so in any event, the IPCC approach is problematic from that point of view, because it's not clear who it's addressed to, but it's also problematic from the point of view of not capturing the full uncertainty in the real world. What the IPCC captures is the model world uncertainty, and the relationship between the uncertainty in the model world and the real world is rather tenuous. There are 2 kinds of uncertainty. There are a lot of different kinds. I'm going to use 2 classifications, which are generally used. One is parameter-based uncertainty, which implies you know the model knows the right physics of the real world, and if you play with the parameters of the model, you can eventually get close to what the truth is. Structural uncertainty generally means the model leaves something big out, or gets something big and fundamental wrong. They basically have the wrong physics, or the wrong chemistry, or whatever. And the difficulty in the climate business is that with regard to some problems, particularly the sea level rise problem, there's a lot of structural uncertainty running around, but we don't have a lot of faith in some of the models that are used to do the projections. There's been a lot of effort, a lot of thinking, trying to improve the situation and ask the question, how can you go beyond this sort of representation of just using the spread of outcomes in the model world to represent uncertainty? Can't we do better than that? It's kind of like the question of asking, how can we represent either the known unknowns or the unknown unknowns? And that, if you think about it, is just very difficult to do in any quantitative way. But that's where the frontier is in this problem, is trying to crack that nut and represent things quantitatively that we don't have to represent quantitatively. And I'll give you some ideas about how to bridge that gap. The IPCC itself has started to bridge that gap by making what are called expert judgments. They're sometimes well thought out after hours, days, weeks, months of deliberation among experts. How do we adjust the range of outcomes in this sort of figure to represent also the structural uncertainty that the models don't represent? Sometimes they're seat of the pants judgments, frankly, that are made at the last minute when you have to write a document and you don't want to say anything that's palpably wrong. So one of the key questions I'm going to address is, how can we develop a better method for quantifying uncertainty, which is not ad hoc, but which is transparent and reproducible? So we have a start on that. If you look at what IPCC has done to represent uncertainty with regard to climate sensitivity, you see a very nice, transparent representation where multiple lines of evidence are brought together to support a coherent picture of what the uncertainty really is, and that's where a statement comes of the sort of the likely range of climate sensitivity is between 1.5 and 4.5 degrees. But climate sensitivity is a more mature field than sea level rise. It's a core of models which are believed to be reliable. They are supported by non-model-based evidence, for instance, paleoclimate evidence, so that one can get the trust in the belief that the climate sensitivity is probably in a certain range. When you get to the details of the climate sensitivity and whether we're judging those correctly, it becomes a different story, and I'll get to that later. So what we want to get away from here is ways to get away from guesstimates about structural uncertainty to get a complete picture of uncertainty. So here I'm going to describe how this question developed in the sea level rise area, a progression of approaches to resolving the problem, and then some ideas that I and my colleagues have had for moving forward at this point. And just to put a little exclamation point on it, you should, for those with a long enough memory, back in the fourth assessment, we've now finished the fifth assessment in 2007, IPCC, when asked to describe the range of uncertainty or the likely outcomes for sea level rise, including the contribution from ice sheets, which is the toughest part, they basically went like this: we don't know. They refused to even provide qualitative language which would answer the question. IPCC made a lot of progress in the fifth assessment report, however. So let's just provide the background. These are figures you're probably familiar with. The top is the global temperature trend. The bottom is the sea level record, gleaned from tide gauges and more recently from satellite data and reanalysis of all that data. And we see that sea level is rising. We understand well why sea level is rising. We don't understand well enough to explain quantitatively the ice sheet contribution to sea level rise. And that's a problem because the ice sheet contribution is now equal on a global basis to the other two big contributions, namely the melting of mountain glaciers and thermal expansion of ocean water. So at a global level, we have a problem because of the lack of a good model to describe the behavior of ice sheets. In addition, it gets worse when you talk to somebody like the mayor of New York City, because local sea level rise, as you've probably heard in other talks, is a more complicated beast than global sea level rise, because there are contributions from other processes beside melting isothermal expansion, namely the non-uniformity of ocean processes, non-uniformity of thermal expansion, non-uniformity of ocean circulation and its effect on the ocean surface height, cross-going gravitational responses, 2 changes in ice sheets, and so forth. I could go on, but I won't. And so the key for this talk is to get at this part of the problem and to look at those models and how, lacking a good model, we can make some reasonable estimates about uncertainty in that climate nevertheless. So here is the projection of sea level rise for this century compared to about 20 centimeters over the last 100 years. And we notice that the global sea level estimates, by the way, the purple curve is basically a low emissions world, which we would be happy to be able to get into, by the way. The orange bundle is basically sort of what many people now believe to be business as usual. It's the RCP 8.5 world, and the colored region around each central line is the 17 to 83% probability range. So basically, there's a 17% chance that sea level rise will be more than 1 meter over the century, according to this reckoning. This reckoning is based on the range of outcomes from the model ensembles driving sea level estimates, with a small expert judgment correction to take account of the fact that IPCC admits it really doesn't know what's going on with ice sheets. When you translate this into a local picture and you think about policy, you can see what the problem is. The global mean range, for instance, for RCP 8.5 is at the bottom, and it's 79 to 121 centimeters after certain corrections are made, which I will talk about. This is some work that's after IPCC, done by Bob Kopp et al., who was also one of my postdocs a few years ago. And you can see that the range of sea level rise, this is the 5 to 95% range, is greater even for specific locations along the east coast of the United States than the range for the global mean. So it's a more severe problem. You go to the mayor of one of these cities, Newport, and you say, well, sea level rise over this century could be 43 centimeters, or it could be, 43 centimeters is what, 1.5 feet, or it could be 151 centimeters, which is 4 feet or something like that. So if I get the numbers right, whatever. 30 centimeters is 1 foot, that's the only. So 5.5. So, what they say, well, how am I supposed to make a decision based on that kind of information? And, the proper answer they might have in their minds, okay, well, then I can wait and not make a decision and wait for these crazy scientists to come out with a narrower range. By the way, this is the variance of those estimates. And you'll notice that the ice sheet, the Antarctic ice sheet contribution in red, and I'll tell you where that came from later, is about half the variance in the global estimate and about a third of the variance in the New York City estimate. So it's a big deal. So if you're not getting the ice sheets right, you can't possibly get the range right, because it's a big chunk of what we call uncertainty. And then, so, how does this translate into what these cities have to deal with? Well, this is an IPCC figure also. And what it does is it asks the question, how often will a flood, which now occurs every 100 years along the coast, occur in the future if global sea level rises 1.5 meters? Now, put aside the fact that storms might change in intensity. Just forget about it. This is same storms as today, but with global sea level increase by whatever it would be at that location, pick a location, if sea level global rises 0.5 meter, which is sort of, is that actually toward the low end of the 8.5. And you can see along this part of the world, you're talking about magnifying that number or increasing the return frequency by a factor between 30 and 100, basically. So that means a storm, a flood, which now occurs every 100 years, occurs every 1 to 3 years by the end of the century. So that a flood of the level of Hurricane Sandy, which was reckoned at the Battery in New York City, and there are different reckonings of this, but let's say it's a 500 to 1,000 year flood, which means in the normal world, the world weren't warming, the sea level weren't rising, we had plenty of time to recover from an episode like that. Well, in the future, you can take that 500 years, say, and divide it by 10 to 100, or 3, by a big factor, and you have an episode like that potentially occurring every few years, assuming the storms don't change, which many people, of course, believe they will change. So this is a very, very big threat to protecting coastal infrastructure if sea level rises as projected. And put another, I'll show you 3 different ways to look at how that translates into an infrastructure decision. These are the 10 biggest flood levels along the coastal flood levels in New York City. They go back 65 years now. And you notice Hurricane Sandy is on the far right, and it was quite a bit above all the other floods, but there were quite a few interesting floods in between. And the dashed red line is the amount of flooding it takes for the water to get inside the New York City subway system. The New York City subway system is the most valuable piece of infrastructure that the city has. It's old, and a lot of the stuff in the city, in the system, like the signal system, is irreplaceable because they don't make those signals anymore. When I say irreplaceable, I mean you can't slap in a new part if corrosion sets in and salt water starts eating away at it. So they don't like when salt water gets in the system. And they got lucky this time. But it's entirely plausible that the next time salt water gets in, it could shut down the system for months. You can only imagine what the economic disruption costs are in New York City. Well, you will notice that among these 10 floods in 65 years, that the other 9 besides Sandy all came within about a foot and a half, maybe 2 feet of getting into the system. So if nothing else changes and you just raise sea level, you're flooding that system regularly unless you think in advance and you start doing some things to prevent the flooding, like temporary barriers when a storm is coming, closing the entrances down, raising the street grades so flood water, even rainwater, doesn't just go in, because it's draining along the sidewalk, but having the air grades higher. There are now plans to do all that, and some of them are actually being implemented. But for someone who's been around and lived in New York City for a long time, I remember the storm in 1992, the December 1992 storm. That was the 100-year storm then, and they went through the same song and dance and the same whining, and we're going to do this, we're going to do that, and none of it got done. And that's because something important always gets in the way, which also costs money. So we have to, this needs to be watched. Not just New York, all these cities, what will they do in response to this risk as the risk is gradually increasing through the century? Just 2 other points. So you could protect the New York City subway system at a moderate expense. By a moderate expense, I mean several $billion, $5 or $10 billion spent over, say, 10 years, you could harden the system. One of the other things that happened during Hurricane Sandy is, this is a little hard to see maybe, but this is nurses evacuating patients from hospital wards because the hospitals were built with the emergency generators in the basement. And that meant when the basements got flooded, as they will tend to do, as the basements do, the generators were not available when the city's power went out. So it is a miracle that nobody died in the process, and now the city is responding very quickly to that, and it made 2 major changes. The building code has been changed, so you cannot build a hospital in a flood zone anymore, assuming they got the flood zones right, which is another story. And the second point is that existing hospitals that aren't going to move have to move the equipment up at a flood level. And that's good, and that's relatively cheap, and most of it is private capital anyway, so the city is eagerly, far more the cost of something else. So again, billions of dollars, but it's doable in a reasonable amount of time. This, however, now here we're talking about a surge barrier as exists, for instance, on the Thames, or even in lowly Providence, Rhode Island, as a surge barrier, because of the 38 hurricane and the early 50s hurricanes. This would cost, conservatively, probably $20 billion, and a lot of people think a lot more, and it would take a lot longer to get done. So the planning horizon that you have to worry about depends on what you're going to plan for. What you're going to plan for depends on what the scientists are telling you is likely, or maybe not the likely, maybe only the 5% outcome. That depends on your own, you as a decision maker, your willingness to accept risk. And you can see it kind of bounces down, so you get a spectrum of what you need to know at what time. And the truth of the matter is that if the world we're looking at requires this, we have to know that about 50 years in advance, because it takes a long time to implement, plan for, and finance, and get done one of these projects. London started building the Thames Barrier, the UK, after a 53 flood, which killed a few hundred people in London and a few thousand people in the Netherlands. The barrier took 30 some odd years to go from a glimmer in the planter's eye to be completed. So if that's what we're into, you know, that's a lot harder to get done. And so the advice that scientists give and their ability to quantify these uncertainties is extremely important. You know, the scientific community more and more thinks that we have to present this in a risk-based framework and tell people the odds and tell people the damages and then let the decision makers make a decision. But I'm not convinced yet that the decision makers are at a point where they absorb or want to hear that information, and that's where that tail cutting off exercise comes in. We'll see. So let's go back to the details of what we do know, what we don't know, and therefore, you know, think further about how we can improve and sharpen our ability to develop, to present a sort of risk-based picture. The fundamental problem with looking particularly at the tails is that the ice sheets, as I say, are making a progressively larger contribution to sea level rise, and they contain a hell of a lot of ice. The Greenland ice sheet, about the equivalent of 7 meters of sea level rise where it all to melt, and it is gradually melting away. It's not clear whether no return has been reached, but it's certainly gradually melting away. If the world warms a few degrees warmer, it will disappear eventually. The West Antarctic ice sheet, 3 to 4 meters of sea level rise equivalent, and the East Antarctic ice sheet, about 52 meters. If you want to worry about East Antarctica, you might think about, well, there was a paper this week that argued hundreds, I don't believe it, because it's based on a model that I don't believe. So I think you're talking more thousands of years. But if you want to talk about what's in the range of decision-making that someone like the mayor of New York City might be worried about, you're talking about something that will play out totally in a few hundred years, in which case you're talking about the West Antarctic ice sheet and possibly a good chunk of Greenland. And so that really puts a point that there's a lot of sea level rise in play, which may be so far out in the tail you don't have to worry about it, or it might be in the 5–10% range, in which case you do have to worry about it. Ice sheets are terribly difficult to model. I won't go into the details about it. This is also something we've heard from various people about before. But the basic problem, of course, is that ice doesn't just melt and go into the sea as water. It also creeps, because the ice sheet is formed when ice accumulates in the center of the cold continent, and then its gravitational force pulls it down and squeezes it out toward the edges of the continent, where it's warmer because of the lower altitude, and where it runs into seawater, which is inevitably warmer than the ice, and you get melting and a whole series of processes, which I won't go into, which are terribly difficult to model. In particular, we have very little idea of what goes on at the base of the ice sheets, and I frankly think we're never going to know what's going on at the base of the ice sheets, and I'll say never, you know, a 50 to 100 year time scale beyond mine. And so we need to have better ways of understanding, probably some statistical approaches, how we're going to model these ice sheets, but none of the methods that are currently available are convincing, except at a regional level. There are parts of the ice sheet where we study enough, where we know enough, where we can start to say sensible things about what's going on at the base and how that controls the flow of ice towards the periphery. And just to show you some of the problems we have now, there's been a big model into comparison for the existing continental ice sheet models. That's a control run for one of them. This is the warming run. This is a control run for another. This is a warming run. You can see these models. I just picked on these two because they were sitting next to each other in the paper. Could have picked on several others. You can see this model has, this is basal velocity, how fast the ice is moving at the base. Very slow velocities in this one, but they go up a lot if you warm the ice sheet. On this one, the control run shows things moving very fast, but then again, it doesn't show things changing much. So these are the kinds of differences in the models, and those differences make it impossible, essentially, to present a credible projection at this point on what the ice sheet contribution is going to be based only on the model world. If you use the the model world information as informative. But due to the variety of problems with the ice, not having the ice physics correctly, not knowing the boundary conditions, not knowing the initial conditions, and not knowing the feedback of the ocean very well, it's turned out just to be a damn difficult problem. So different people started looking at different approaches for estimating what was going on with the ice sheets that were not based on the usual process-based models that we've gotten so used to, and which dominate the estimation of future warming, say. The first set of estimates were called semi-empirical estimates. These are essentially fancy ways to take the historical observed behavior in sea level and extrapolate it into the future based on some simple assumptions of it being linear or and sometimes a more complicated relationship with temperature. In other words, finding an empirical relationship between temperature change, global temperature change usually, and sea level rise, and then projecting that into the future using the projected temperature changes from the AOGCMs. And this, for a few years, looked like a promising approach until IPCC came in and dismissed it entirely, I think prematurely, because it did not have a good way to represent the uncertainty. It basically, it's represented today, the semi-empirical representation of uncertainty was basically a representation of the uncertainty in the statistical model, and did not combine that with the uncertainty in what people actually thought the ice sheets, for instance, might actually be doing. It was a top-down method in that it looked not at the different components, thermal expansion, glacial contribution, mountain glaciers, ice sheets, but looked top-down and measured it from sea level to sea level globally. Therefore, no one could foresee a way to make local projections from that, and basically it's been shelved. It has a lot of ardent proponents, and I think it's been prematurely shelved, but IPCC spent a couple of pages saying why this was a bad method, okay? And it didn't use it to estimate uncertainty. Second method that is proposed is called the kinematic approach, and basically Todd Pfeffer sat down and in his head tried to outline what's the fastest that an ice sheet could move in the fastest, in the warmest, under the most favorable assumptions for the ability of ice to move in a warmer world, how fast could it move? And he developed an approach which took the fastest moving basins in Antarctica plus the Greenland ice sheet and tried to estimate a sort of worst case. So this is a bottom-up approach because it's looking at it in terms of individual ice sheet basins. And it's useful because it kind of bounded the problem, at least temporarily, at about 2 meters of sea level rise from the ice sheets over this coming century. Since then, higher upper bounds have been estimated, most famously or infamously recently by Jim Hansen, who threw out a number of something like, I don't know, 5 meters in 50 years, which is not credible in my first view, and didn't have a lot of backing behind it. But in any event, that kind of thinking, what's the worst we can make the system do, is what these kinematic approaches tell you. But the trouble with that is, again, do policymakers want to know worst cases? Some do, but some are going to go around and throw out worst cases because they're so bad there's nothing they can do about them. So in the hope that rationality governs government, there is the ever idealistic desire among scientists to produce a more fulsome set of information, so that another group of people went about figuring, okay, let's throw away the process-based models. Let's not look at them. Let's throw away the upper limit kinematic approaches. Let's throw away the semi-empirical approaches. Let's just get a bunch of experts together and ask them what's called structured expert elicitation, what they think is going to happen, because it's as good as any other method that's used. And this way of doing things is IPCC hates it as well. It's not clear why, except maybe it's competition for IPCC. I'm not entirely sure. I spent a lot of time at IPCC, and I can't always figure out why things are the way they are. But a group of people led by Jonathan Bamber brought together scientists on 3 separate occasions, ice sheet experts, to get them under controlled conditions to discuss and then make estimates of what they thought the ice sheets were going to do, and to produce a full distribution of probability of the ice sheet component of the discharge. This dealt with the full ice sheet, both ice sheets. It was fully probabilistic, and it didn't just bring in people and then ask them to write down their best guesses. It asked a series of structured questions which lead them logically through what you would need to put together in your head to make an estimate of what ice sheets are going to do. And it threw in some seed questions, like what's been the mass balance of Antarctica over the last 20 years, or the last 50 years, or the last 100 years, so that the opinions of the experts could be weighted and judged against what they knew, according to the scoring method. It's an interesting method, and it has an interesting heritage. It's actually been used, and I'll get to this later toward the end, at the very end of the talk. It's actually been used successfully, for instance, to make sure that in the space program, the rocket, the ship was actually going to hit the moon. It's been used in the early design of airplanes to make sure that we had the specs right and weren't going to crash. It's been used probably slightly less successfully in the nuclear reactor safety business. And a few other, it's been used to determine the parameters of air pollution plume models, where it's been applied very successfully actually to improve the estimates in the process-based models and make them more fully reflect what's going on in the world. So we know expert elicitations can work, and in some cases work better than the process-based models that are supposed to be giving us these projections. Anyhow, that brought us to the point in the middle of the fifth assessment where IPCC had to choose between these various methods. And again, my postdoc, Chris Little, in conjunction with several collaborators, including me, came up with yet a fourth method. And it was this fourth method that IPCC eventually adopted. One reason, for Antarctica, one reason they adopted it is because it got through peer review in time, and some of the other proposed methods did. In fact, they never got through peer review, so we were just sort of the last man standing, you might say. So what did we do? What was our view, and how was it a little different from others? First of all, we used multiple lines of evidence. We developed a simple kinematic model, where we developed the model for each basin of Antarctica, and there were 19 of them. Secondly, we were able to combine it with the empirical methods by using the recent behavior, the recent meaning over the last 20 years of the ice sheet, because we have good measurements for how the rate of ice was from each of these 19 basins. And there are other measurements from other sources for the mass balance of the continent as a whole. We also took advantage of the fact that there is one area of Antarctica where there happens to be a pretty good process-based model, and that it's credibly reproducing what the ice flow in that region is doing. It's called the Pine Island Glacier. And we put therefore together three sets of more or less independent evidence and try to build a model based on that set of evidence. Then ran a bunch of Monte Carlo samples, 10,000 of them, to try to produce a statistical distribution, weighting the samples according to how well they reproduce the actual total mass balance of Antarctica over the period, and we generated in that way distributions, which is the kind of information that we want to be able to give the policymakers. The warning, you can find it in IPCC in Chapter 12, Box 2, is basically, it says, we actually don't know how to combine independent lines of evidence. There's no consensus on how to do it, so this is sort of the cutting edge. There's the roadmap there's the model on the left. I won't go into great detail about it, but basically there are two terms. One determining, reflecting the surface mass balance, which in Antarctica is, since there's no melting by and large, it's just basically the accumulation of precipitation on the ice sheet. The other, the loss, basically through dynamic discharge. What we're doing with this exercise is fitting the coefficients in this model to the observed data using a Bayesian approach with the Monte Carlo method, and then projecting forward to say what the ice sheet would do over this coming century. When you do that, that just shows the routing of the methods, the recursive method. I won't go into the details, but basically what it shows is more or less what you'd expect. Namely, there are certain basins, the black basins there, which are basins of Pine Island Glacier and Thwaites Glacier, which are moving fast now, and which we expect to be moving fast in the future and contributing positively to the mass balance. That is their contributions to the line at zero. There are other basins all around the periphery of Antarctica, which on average will contribute negatively to the mass balance. Those are the ones below zero. But you see in a probabilistic representation that there's a considerable amount of weight above the zero. So if you were just looking at what the average contribution from the basin would be, you'd say, forget about it, it isn't important. But if you're looking at a probability distribution for the outcomes, you've got a hell of a lot of probability. So that's a thing that has not been paid any attention to in the past, that when you really do these things probabilistically, you're going to pull the distributions probably in favor of larger Antarctic contributions. So the Antarctic contribution we got out of that was about 13 centimeters over the course of this century. It's not a lot compared to some of these upper limit contributions, but it was a lot more than the process-based models were producing. This shows you what the models. These are the estimates. This is our estimate. It's in here. It's between about -10 and plus 13 centimeters. This is the 5 to 95% range. You can get a negative contribution because accumulation could win over the dynamical discharge. These are the semi-empirical and upper limit type approximations. They're quite a bit higher. But since the process-based models were coming in down here somewhere for the next 100 years, we had sort of moved in, I don't want to call it the right direction, but the direction of a larger Antarctic contribution. Yet we were unsatisfied, because what this means is that there was, in this, I'm sorry, let me go back. The expert elicitation also came in this range. What this meant is there was a lot of expert opinion which said there was something left out of our model. And what was left out, I'll get to that in a second. Those are just the overall IPCC estimates. What was left out is we made the assumption that there would be no outright collapse of the ice sheet. We made the assumption that none of the basins we looked at around Antarctica would collapse relatively instantaneously, meaning losing most of their mass over the course of several decades. And that is, because we left that out, when IPCC took our estimation method, they said, well, this doesn't really cover the very likely range, 5 to 95%. It covers what we think is rather the likely range, 17 to 83%. What this means is there's roughly 17% likelihood of a much worse outcome than 13 centimeters of sea level rise from Antarctica. So we went back then and developed another method. And this new approach, in this new approach, we decided to bring in the expert elicitation to try to see if we could learn something from comparing what the experts say in this elicitation phase to what our simplified model says, and see if we could pull the model in the direction of what the expert elicitations gave us. And this is a useful thing to do for several reasons. It gives you an answer. It allows you to adjust your model to reflect fully expert opinion. It allows you to ask what you would have to do to your model to make it match expert opinion. And then it gives you, at a basin by basin level, a way to project into the future, and in fact allows you to project outcomes at the basin level, which then can be compared to what actually happens in the real world. And at the same time, by using this formalized structured expert elicitation, it allows you to avoid the ad hoc process of 6 people sitting in a room under pressure to produce a report and deciding at the last minute that they have to adjust the probability ranges and not having a rule book for how you do that. So it's a formalized way, it's reproducible, it won't necessarily give you the same results if you use the same group of experts, but that's something that can be tried and you can see if your results converge. So these are the kinds of probability distributions that the experts give. This is from the Bamber and Aspinall expert elicitation. Antarctica is sort of the red and pink in here, and the green is East Antarctica, the red and the pink are West Antarctica, and they show you, this shows you the probability of various rates of sea level rise, and you'll notice that some of these, that the tail is quite long and remains quite thick. If we actually got these rates of sea level rise later in the century, then some of the higher predictions of multi-meter sea level rise in the century would come true. So what we wanted to do was take this distribution, combine it in some way with our simplified model, and pull the model into being in agreement with the distribution, and see what that implied at the basin level. Now, to go back on structured expert judgment, there are a few things we know about these kinds of elicitations. Individual experts are not very accurate when they make predictions of things like what's the ice sheet going to do. And they're not very informative either. Informativeness is the ability to concentrate probability in a narrow range. So they're basically individual experts that give you fairly flat distributions sometimes, and they'll be inaccurate because they'll keep you in one place. But if you then weight those according to performance, what I told you a few minutes ago about the ability of an expert to predict something that's in sample, something you already know, you can improve the performance of these expert elicitations. And if on top of that, you not only weight the distributions, you not only average the distributions of different experts, which improves performance, but you weight them according to what I just described, you can get very good results. And it's that kind of process which has been used again in aviation, space exploration, nuclear safety, etc., to with fairly good results, improving in retrospect on what the models were able to project. So we thought we would try the same thing too. And Roger Cook came up with this idea of what's called probabilistic inversion. Inversion techniques are probably fairly familiar to everybody in this room. You take some observables, for instance, the carbon dioxide concentration distribution in the atmosphere geographically, and then you invert it, and you can obtain information on either unknown or unobservable or model-related quantities. For instance, what's actually coming out of different smokestacks at different locations on it. Or, for instance, it's been done in the ice sheet business by taking the velocity of a glacier and inverting it in order to find out things about how rough the base is, even though you have no direct way to measure what's going on at the base. Probabilistic inversion is a more complicated technique which takes a probability distribution or set of distributions for the behavior of observables and inverts it on the model to give you the probability distribution for parameters in the model. So this is what we did. We took the distribution from the expert elicitation and inverted it, and it holds the model parameters to be in agreement with what the experts think is the right answer. The experts are judging it based on the cumulative discharge from the whole ice sheet, but what the information we get out of it is what's going on in individual basins. And it turns out the result was that you have to really accelerate the ice sheet a lot in one key basin, particularly the Thwaites Glacier Basin, which is right over there, in order to get the ice sheet to behave right. And there's been a long strain of thought in the community that this is a basin that's about to collapse, and that could contribute 1 to 1.5 meters of sea level rise if it does. These are the distributions that we got. What you can see is that before the inversion, you get a very broad distribution that, and then like this, and there's a fair tail, but it still goes really rapidly to zero. After the inversion, you sharpen the peak, you decrease the likelihood of Antarctica giving having a positive mass balance, that is, of either discharge slowing down or accumulation winning, and you increase the density of the tail. That's for Antarctica as a whole. This is West Antarctica, this is East Antarctica. And again, that kind of information propagates back to the process-based level. These are each of the 10,000 simulate Monte Carlo samplings. And what you can see that happened is the original distribution before the inversion was sort of symmetric about the axis, and what this did is it pushed the distribution into this quadrant. These are the tail episodes with a lot of very fast discharge. That's basically the collapse of the Thwaites Glacier. This here is the elimination of what's happened here is this quadrant, which would have Antarctica having a positive mass balance, basically goes away. And so that was a result. It gives you some physical insight into why the experts believe what they do and what you would have to see happening in the model to get it to be so. And again, all of this assumes you don't have a good process-based model to lean on. And this basically is another way to look at the probability, which basically says when you get that down into the tail, the inversion tells you that you have to have a lot going on the weight score. So what do I conclude from this? First of all, this is only one possible approach. Many other people are looking for ways to quantify the ice sheet behavior in advance of us having a good, reliable prognostic model. For reasons which I don't fully understand, IPCC's reaction previously to using expert elicitation has been that they don't, because the experts base their opinion on the same studies as we assess. What that means is 6 people sitting in a room after a long enough time coming up with some estimates can give you a better answer than people who have to obey some sort of guided pattern of reaching a conclusion, and where there's no weighting process to determine whether you've got the right experts in the room to begin with. And I just don't believe that. So I think it's time for IPCC to change. I think it will change and take advantage of some of these other tools that are available. I think this method will be useful for other areas where there's no reliable process-based model. For instance, questions around the release of methane from the tundra, or the methane hydrate problem. And even with even using more complex models, models that we have some faith in, and where arguably the central model-based range is telling you something credible, there's all the stuff about what's going on in the tails, which there's a lot of controversy about, even in, or in particular, in the projected future temperature, or with regard to climate sensitivity, in other words, where I think this method can be useful. So, to conclude, I think we've just begun scratching the surface and trying to understand how to deploy expert judgment. That the climate business is way behind because this stuff has been used effectively in other fields, which also, where people's lives are also involved, like shooting people at the moon, and that it's time for the community to catch up. Thank you. Any questions? Henry?
Obviously, the expert judgment becomes better if the weighting of the performance is appropriate. But then the question is, what's the criterion that's better there? Because since you want, in some sense, to have a realistic notion of the spread, it's not necessarily that decreased spread in the total.
Right, so it's the same problem with science. So the question is, how do you know what questions to ask experts to know if you're judging the right sense of judgment that's going to give you the answer to the problem you want?
I'm asking more specifically, how do you decide on your weighting algorithm to weight the performance-based part?
In other words, how do you decide if somebody answers the question wrong, do you throw them out entirely, or do you de-weight them? I think different approaches have been used in different cases. What you really want to do is put a little money into this, get different groups together, answering different sets of questions, and try to learn a little bit about what works and what doesn't. After all, we've got the same thing in the current approaches to using the model ensembles, uncertainty, where we're trying to weight model, experience weight models. And that hasn't been very successful, because it turns out, if you say you want to project temperature, so you weight models according to their performance with projecting maximum temperature in the last 50 years of the record, that might give you a good projection of some things, but if you ask the same model to project precipitation, it does a terrible job. So it's the same question, only you're asking it of people instead of the computer models. And what you need is the same thing. You need to run a lot of returns. You need to compare them to experience, and you need to learn a little bit about how to implement the technique. I'm not familiar enough with what was done in, say, nuclear power safety to give you a straight answer to how they resolve that question. But I can find out. Anybody up there? Yes. Yeah.
These papers came out saying because of the interaction of the warmer water, ice sheet melting is inevitable over a long period of time. Is that none of the things
Well, that question of, let me back up. The fate of the ice streams, particularly in West Antarctica, but to some extent East Antarctica, is determined in part by how fast the ice shelves they form are melted as they protrude over the continent into the warm waters of the Southern Ocean, the circumpolar ocean. And that we're not able to model that process very well yet either, but that's the kind of thing the experts, if you have the right experts, are thinking about when they make these judgments. That part of the problem isn't modeled well either, but it is generally now believed that that's what's driving the rapid loss of ice in the two black basins I showed you, the Thwaites, the Amundsen Sea Basin, the Thwaites and Pine Island glaciers.
So do those papers dealing with long-term melt, do they have any bearing?
You're referring to this paper that just came out last week?
Well, this was earlier in the year, it basically said it was inevitable.
Oh, the Renault paper. Yeah, inevitable is not a word I like to use when we're talking about 1,000 years from now. So, yeah, I mean, they're talking about the end point of that process, but then it goes through a series of assumptions. The next question is, if you lose the 1.5 meter sea level rise equivalent worth of ice behind the Pine Island and Thwaites glaciers, what does the rest of the ice sheet do? Does it come squirting right through that divide and go and reroute the ice from, instead of draining into the Ross Sea, draining the Amundsen Sea and draining very quickly because there's nothing holding it back anymore? The answer is, we don't know. What we do know is the beginning of that process is well underway, and there's reason to believe that it might be unstoppable. But nobody put probabilities on that. See, that's something to be done. Yes?
Just one clarification. Earlier in the presentation, we had a graphic that showed the contribution of different components of sea level rise and variance. And I think you had a graphic for both New York City and Atlantic City, and I was a little surprised. I thought that
that one?
Yeah.
What do you mean that one?
So the one that you were just the Greenland ice sheet accounts for a relatively large amount of variance in the global and then in New York City.
Yeah.
It's very little.
Right, and it's New York City is not a good place to take for this either, particularly because of the effect of the meridional overturning circulation and its effect on sea level in New York. It's a special case, but this is just a for example. The point is that many locations throughout the world, the ice sheet contribution is the biggest contribution to the variance, and therefore you have to worry about that when you try to talk about the uncertainty.
Where's the bottleneck in incorporating elicitation in the IPCC? Is it author teams? Is it could this new election of becoming chair influence?
Well, it could be the current chair, the future chair would have a different view. I've spoken to several of the potential future chairs, and I think as of today they have a different view. But institutions are big,
it's not
heavy,
in the
and hard.
mandate that they can't. There's nothing in the mandate.
There's no
that they
rule.
can't do.
It's a lack of inventiveness, lack of being willing to be innovative that characterizes all big institutions. And one of the worst things, I'm very happy IPCC won the Nobel Prize, Peace Prize. I have a little plaque in my office for that. But in a way, it was the worst thing that ever happened to IPCC, because it takes itself very seriously now. So it's a problem with any institution, but there is some hope that several of the people running for the new chair will see it differently. And this isn't the only issue area where IPCC has issues. One more?